Hello guys, welcome back to my channel Gamma Die Gamma. And in this video, I would in this video and videos after a few videos after this, I will be solving the ISC 2020 math exam. And interestingly, I sat for this exam in around February or something, and happened to score a perfect score of 100 over 100. And I'm saying that so that you have less reasons to doubt this paper solution video that I'm making. Okay, so let's get started. So in this video, I would like to cover not all, but I think half of section A, a part of section A. And naturally, we'll start with question number one. Now, question number one has 10 subparts. So let's do subpart one. So the question is saying, um, it's basically telling us to determine whether the binary operation denoted by this asterisk on R, the set of real numbers, defined by A asterisk B is equal to absolute value of A minus B is commutative. We need to determine whether this binary operation is commutative, and then after we've done that, they're telling us to find the value of negative 3 asterisk 2. Okay, so let's get started now. So we know that uh, A asterisk B is given by A minus B modulus absolute value. So now what I'm going to do is let P comma Q be two elements of the set of all real numbers such that they satisfy the binary operation P asterisk Q is equal to by definition absolute value of P minus Q. So let them satisfy this. Let P and Q satisfy this operation. So for commutativity, we need to show that, well, P asterisk Q we know satisfies some this binary operation, but for commutativity we need to show that P asterisk Q is the same thing as Q asterisk P. So we know that um, our left hand side holds true. So let's look at the right hand side, which is basically Q asterisk P, and by definition that it will be absolute value of Q minus P. Now what I can do is I can factorize a negative up front and then flip this order to make it P minus Q. But since we have a negative inside an absolute value, it's like it doesn't matter what we have inside the absolute value. It can be a positive number, a negative number. The absolute value just sucks up the negative. So this is the same thing as absolute value of P minus Q, which from this equation 1 we know is P asterisk Q. So the RHS, that was Q asterisk P, is equal to P asterisk Q, which is nothing but the LHS, the left hand side. So RHS is equal to LHS. Hence, the binary operation is commutative. Because it satisfies this. That's why. Okay, so now second part is telling us to find the value of negative 3 asterisk 2. So negative 3 asterisk 2 will be absolute value of negative 3 minus 2. So that will be absolute value of negative 5, which is just positive 5. So there we go. This was a really nice question on binary operations, and yes, we've done that. Okay, so the next stop is question 1 subpart 2, and it's, you can see, is already a proving question. So we need to prove that tan squared of sec inverse of 2 plus cotangent squared of cosec inverse of 3 is equal to 11. So naturally, looking at the robust left hand side, let's start from there. So we have tan squared of sec inverse 2 plus cotangent squared of cosec inverse 3. Fair enough. Now I would like to use some square identities of trigonometric functions. So notice that tan squared of some angle theta is equal to secant squared theta minus 1. Same thing with cotangent squared theta, which is cosecant squared theta minus 1. So when we do that, we have secant squared of secant inverse of 2 minus 1 plus cosecant squared of cosecant inverse of 3 minus 1, and this can be expressed as secant inverse of 2, the whole thing squared, and this will be minus 2, plus cosecant of cosecant inverse 3, the whole thing squared. And this, the trigonometric function and the inverse trigonometric function cancel off to just give us 2 squared, which is 4 minus 2, and this will be 3 squared, which is 9. 9 plus 4 is 13, minus 2 is 11. That's our right hand side. Hence proved. Okay, so question 1 subpart 3. It's saying without expanding at any stage, find the value of the determinant, and you have a delta which is equal to this determinant matrix over here. So now, without doing any other observation, we can see that there is a 20 on this column. So let's plug out 20, and we can do that for any single column when we're talking about determinants. So we've 1 1 1 because we factored that out, and a b c b plus c, a plus c, a plus b, all as it is. Now I would like to go ahead and change column 2 to column 2 plus column 3, and I can do that. These are nice properties of determinants that we need to use because we can't expand according to the question. So C2 plus C3 will be A plus B plus C. Same thing here, A plus B plus C, A plus B plus C. I'm just adding this column and this column. And then third column is as it is, A plus B determinant. Now, just like I pulled out the 20, I can pull out the A plus B plus C from this middle column. So I have 20 times A plus B plus C, and then I have 1 1 1 1 1 1 B plus C, A plus C, A plus B. And now, noticing that the first column and the second column are equal because they have ones in them, we can conclude that the determinant is 0. Again, this is a property of determinants, that if two columns or two rows are identical, then the entire determinant comes out to 0. So the answer is 0. Okay, next is question 1 subpart 4. So we have, if two matrices multiplied with each other is equal to some resultant matrix, and they're telling us to find x. So this is a classic matrix multiplication problem, and this is really easy to do. So let's just directly multiply the left hand side that we have here. So if I do that, I'll have to go this row this way in the direction of the arrow, and then down this column like that, and the consequent terms go multiply with each other, and then you add the remaining terms. So we'll have 2, which is the first term, on this arrow trail, times 1, which is the first term on this other arrow trail. So 2 times 1 plus then the second term times this second term, 3 times -2. Okay, then we are done with this uh, entry. Now we still use the same row but go down a different column now. So now the first entry is -3 over here. So we have 2 times -3 plus 3 times 4. Okay, so we are done with the top row. Now go down to the bottom row. So 5 times 1 plus 7 times -2. That's one entry. And then look at the other column. So 5 times -3 plus 7 times 4. And all that is equal to -4, -9, 6 and x. So when I actually do the math, I have -4, -9, 6 and 13 is equal to -4, -9, 6 and x. So you can see that all the other entries are same, -4, -4, -9, -9, 6, 6. But instead of x, we have a 13 here. Therefore, x is equal to 13. Just comparing the two matrices. So now question 1 subpart 5. We have to find dy over dx if x cubed plus y cubed is equal to 3axy. So it's good old differential calculus. I've made an entire playlist on this. You could probably refer to it if you don't know what I'm talking about. So now what I'm going to do, take this expression and then differentiate both sides with respect to x. So when I do that, I have 3x squared plus 3y squared times dy over dx by implicit differentiation is equal to 3a, and the product rule, if I do that, I have y plus x times dy over dx. So we can cancel 3's from all sides. So we'll have x squared minus ay is equal to dy over dx times 3ax, sorry, no 3, ax minus y squared, and then dy over dx just becomes x squared minus ay divided by ax minus y squared. So that's the expression for dy over dx that we intended to find. Moving on to subpart number 6. It says the edge of a variable cube is increasing at the rate of 10 centimeter per second. How fast is the volume of the cube increasing when edge is 5 centimeter long? So first of all, what we do is we convert this word problem, actually a related rates problem, into the language of math. So to do that, let's call edge to be x. So they're saying the edge increases at a rate of 10 centimeter per second. So it's basically hinting at derivatives. So dx over dt, and t is time. So the rate of change of edge with respect to time is given to us as a constant rate of 10 centimeter per second. Okay, that's given. But what do we need to find? They're telling us find the volume of the cube. So let's call the volume v. They're telling us to find the rate of change of volume. How fast is the volume changing, or rate of change of volume, but not generally when edge is 5. So when x equals 5. Okay, so how we know x dx over dt, and we have to find volume. How are volume and edge length x are dependent on each other? So for a cube, v is equal to x cubed, right? The volume is equal to cube of the edge length. And now when I differentiate both sides with respect to t, I have a dv over dt is equal to 3x squared dx over dt. Now I'm just going to plug x equals phi like we had to find in this. So we have 3 times phi squared, which is 25, times dx over dt is constant irrespective of any x, which is 10. So the final answer is 750, but this is volume per unit time. So the unit will be centimeter cube per second. And the unit is important, so please don't forget that. Okay, subpart number 7. Finally, and luckily, we have a definite integral from 4 to 5 of the absolute value of x minus phi dx. So in such integrals, definite integrals where you have absolute value concerned, you look for when this inner function, here it's x minus phi, is positive, when it's negative, and when it's 0. So since this is a linear function, it will have one place where it is 0, and then beyond that given value of x, it will be positive, and below that given value of x, it will be negative. It will basically be a line that's something like this. Some value of x, it will be 0. Some, beyond that value of x, it will be positive, and before all that value of x, it will be negative. So let's just tweak this. So x minus phi is 0 when x is equal to 5. So before 5, so when x is less than 5, x minus 5 is negative, and when x is greater than 5, x minus 5 is positive. Okay, but now notice on the interval of integration, which is going from 4 to 5, it will be negative from 4 to limit as x goes to 5, and then after that point at 5 exactly, it will be 0. So it doesn't matter if we ignore exact point of 5, because you can write this as integral from 4 to 5 of x minus 5 dx, and this is the limit as x goes to 5 for this. And then from that from that limiting limit x point to actual 5, x minus 5 dx. But the thing is, when x equals 5, this term is anyways going to 0. This becomes 0, and on this interval this is negative. So absolute value of something that is negative, we can lose the absolute value if we write a negative associated with it. Integral from 4 to 5 of x minus phi dx. See, we lost the absolute value, but we took a negative to compensate for the negative area we'll be getting, because originally we had an absolute value, and absolute value doesn't tolerate any negatives. So this negative and then this negative will make a positive, you'll see. So when we integrate this, we have negative x squared over 2 plus 5x evaluated from 4 to 5. So when I plug stuff in, I have negative 5 squared, or negative 25 over 2, plus 5 times 5, which is 25, minus negative 4 squared by 2, which is negative 16 by 2. 5 fours are 20, so add 20. This simplifies to 25 over 2 minus 12, which comes down to 0.5 or a half. So that's basically the value of the integral. And it turned out to be positive because this negative and then this expression also became negative from these inequalities. That's why both the negatives cancelled out, and since we couldn't tolerate any negative areas due to the original absolute value, we got a positive answer just as expected. Okay, subpart 8, they're telling us to form a differential equation of the family of curves y squared is equal to 4ax. So we first, the basic idea of making a differential equation is to check how many constants there are. So a is a constant. So how many ever constants there are, those many derivatives we need to take. So since there is one constant, the highest order differential equation you can form therefore is allowed is of order equal to the number of constants there are. So order 1 because there's one constant. If there was a and b, then the highest order of differentiation of forming the differential equation would be 2. So in any case, we have y squared is equal to 4ax. Let's differentiate both sides. So differentiate with respect to x. So we have 2y times dy over dx is equal to 4a. But the thing is, our differential equation should not have constants. We need to get rid of the a. So how will we do that? So we can rearrange this equation. Take the x on that side. 4a is equal to y squared over x. So make that substitution over here. 2y times dy over dx is equal to y squared over x. And one of the y's cancel out. This means we have a dy over dx, taking the 2 underneath, y over 2x. That's our differential equation. Nice and simple, separable differential equation. And if you don't believe me, you go ahead and solve this differential equation. You'll get the same answer. Okay, so subpart 9, a bag contains 5 white, 7 red and 4 black balls. If 4 balls are drawn one by one with replacement, what is the probability that none is white? Okay, so we have a probability question now. So now none is white. So the thing is, we need to separate between white and non-white balls. So let's have say 2 containers just for our understanding. We have 5 white here. So these are white balls. And here we have non-white balls in the second container. It's ironic that I write this with a white color, but anyways. So in that we have 7 red and 4 black. So in all, 11 non-white balls. And 5 white balls. And since we are drawing them one by one, we just can't select from, we can't select 4 from 11. We can't do 11 choose 4 directly. It's going to be a stepwise process. So our probability that none are white when you draw 4 balls one by one with replacement will be, okay, first you draw one from the 11 because you're not supposed to get white. So to not get white, you'll draw one from the 11 on your first chance. So 11 choose 1 divided by the total number of balls there were. So 16 balls, right? So 16 choose 1. That's the probability on your first turn picking balls. And then when you picked a ball, you place it back because there is replacement, right? You're replacing it back. So the 11 non-white still remain 11 non-white. You don't lose a ball because you're replacing it in the second turn. So you get 11 C1, 11 choose 1 divided by 16 choose 1. That's the second term. And then similar for the third term, 11 choose 1 divided by 16 choose 1 multiply with, and the last term you again obtain the same thing, 11 choose 1 divided by 16 choose 1. And why did I multiply? Because it's successive turns, successive 4 turns of drawing balls that you are having, right? So successive 4 turns of drawing balls. So it's first turn and second term and third turn and fourth turn. So you obtain 11 times 11 times 11 times 11 4 times. So 11 to the fourth divided by 16 to the fourth. That's your required probability of, you know, obtaining no white balls in 4 turns of uh, replacement if you take the turns one by one. Okay, so finally we have the last sub part of question number 1. So it's saying let A and B be two events such that probability of A is half, probability of B is small p, and probability of A union B is 3 over 5. So find small p if A and B are independent events. Okay, so let's look at the given stuff. Probability of A is half, probability of B is small p, and probability of A union B is 3 over 5. So probability of A union B, and there was a formula for this in elementary set theory, is equal to probability of A plus probability of B minus probability of A intersection B. That's basically removing the overlapping part. Okay, so we have probability of A union B turning out to be 3 over 5. We have probability of A to be half, with probability of B to be small p, and probability of A intersection B is not given to us, but something else that is really really important, without which this question would be impossible, is given. They're telling us the events A and B are independent. So for two independent events A and B, in this case, probability of A intersection B is equal to probability of A multiplied with probability of B. This we obtain by the logic of conditional probability, which says the probability of A such that B has occurred is equal to probability of A intersection B over probability of B. Now, if A and B are independent events, probability of A such that B has occurred will simply be probability of A, because A is not affected by whatever B turns out to be. So probability of A, and then when you multiply probability of B, that is equal to probability of A intersection B. So that's where we get this formula from. So in place of this intersection, we can just have probability of A times probability of B, which is P times half, which is P over 2. So then we have 3 over 5 minus half is equal to P minus P over 2, which is P over 2. And that turns out to be P is nothing but 1 over 5. You can do the basic algebra on a separate piece of paper if you want, because this LCM turns out to be 6 minus 5 over 10, or 1 over 10, being equal to P over 2, and when you take the 2 on that side you have 1 over 5. Okay, finally we move on to question number 2, that says if the function f defined from real number to real number be defined as f of x equal to this expression, and g defined from r to r be defined as g of x some expression, so that g composed of f of x is equal to f composed of g of x. So let's look at the left hand and the right hand side separately. So the left hand side, is g composed of f of x, which can be represented as g of f of x. It's a composite function. So what I'm going to do is replace f of x with this expression that we have, 3x plus 4 over 5x minus 7, and now I'm going to write g, but in place of x in this g, the definition of g, I'm going to put this rational function which represents f of x. So 7 times 3x plus 4 over 5x minus 7 plus 4 divided by 5 times 3x plus 4 over 5x minus 7 minus 3. So now taking the LCM quickly, we have, opening the bracket, 21x plus 28 plus 20x minus 28 divided by 5x minus 7, and then in the denominator still we have 5 times 3 is 15x plus 20 minus 15x plus 21 divided by 5x minus 7, and the 5x minus 7 cancel out. So we have the 28's cancelling out and the 15x is cancelling out. So 21x plus 20x is 41x divided by 41, which is simply x. So that's the left hand side we cared about. Now let's look at the right hand side. It's f composed of g of x. So f of g of x. So in place of g of x, we just substitute its definition. 7x plus 4 divided by 5x minus 3. And now then use the definition of f. So if 3 times, in place of x, we plug in this rational stuff. 7x plus 4 divided by 5x minus 3 plus 4 divided by 5 times 7x plus 4 divided by 5x minus 3 minus 7. So again, as always, take the LCM, open the bracket, 21x plus 12 plus 20x minus 12 divided by 5x minus 3, all of that divided by 35x plus 20 minus 35x plus 21 divided by 5x minus 3. Denominators cancel, 12 cancels out, 35x cancels out. We have 41x over 41, which just turns out to be x, and that's the right hand side. So left hand side is equal to right hand side, and that's exactly what we needed to show. Yeah, that's it. Okay, moving on to question number 3. It had two parts, so you could do either. There was an option for this. So I'm going to do both of them. So question number 3 was this proof. If cosine inverse of x over 2 plus cosine inverse of y over 3 is equal to theta, then prove that 9x squared minus 12xy cosine theta plus 4y squared is equal to 36 sine squared theta. Now to approach this, let's look at this expression, cosine inverse of x over 2 plus cosine inverse of y over 3 is equal to theta. Take sine on both sides. So we have sine of cosine inverse of x over 2 plus cosine inverse of y over 3 is equal to sine theta, and then use the compound angle formula for the sine. So sine of the first angle, sine of cosine inverse is square root of 1 minus this angle squared, so x squared over 2 squared, which is 4, times the cosine of the cosine inverse of y over 3 is y over 3, plus now just reverse the whatever was inside the square root and what was outside. So if x over 2 outside times square root of 1 minus y squared over 9 is equal to sine theta. Taking a common denominator, we'll have 2 come out with the 3, so 6 y over 6 times square root of 4 minus x squared plus x over 6 times square root of 9 minus y squared equal to sine theta. And now let's actually square both sides. So when I do that, I have y squared over 36 times square of this is 4 minus x squared plus 2 times xy over 6 times 6 36 square root of 4 minus x squared square root of 9 minus y squared plus x squared over 36 times 9 minus y squared is equal to sine squared theta. So let's put 36 on that side. 36 sine squared theta is equal to 4y squared minus x squared y squared plus 2xy times square root of 4 minus x squared times square root of 9 minus y squared plus 9x squared minus x squared y squared. So we have 36 sine squared theta is equal to, and it's almost starting to resemble this expression. So we have 9x squared, then we have this other expression of minus 2x squared y squared and then 2 here, which we can clearly factorize out. So 2 times xy times square root of 4 minus x squared times square root of 9 minus y squared minus x squared y squared plus 4y squared. Okay, so now what I'm going to do is look at this term, pull out xy. So we have xy and then multiply and divide by 6. So 6 times 2 is 12xy, and it's actually matching with this 12xy. And we have square root of 4 minus x squared times square root of 9 minus y squared. But we have to divide by 6 because we multiplied by 6 originally. So take a 2 here and take a 3 here because 2 times 3 is 6. Minus x over 2 times y over 3 again. See, we can split 6 like this plus 4y squared. So this turns out to be 36 sine squared theta. It's not even 9x squared plus 12xy. We can take the 2 inside. We get square root of 1 minus x squared by 4. Square root of 1 minus y squared by 3 minus x by 2 times y by 3 plus 4y squared. And I would suggest taking a negative out as well so we can switch the order of these things. Okay, so we have the negative 12xy in place, but it's suggesting that this term is cosine theta, and we can show that actually. We can actually take this expression, this call it equation 1, take that, take cosine on both sides. So we'll have cosine inverse of x over 2 plus cosine inverse of y over 3 is equal to cosine theta. Cosine theta using the compound angle formula will therefore be x over 2 times y over 3 minus square root of 1 minus x squared by 4 times square root of 1 minus y squared by 9. So we can substitute that over here. So we have 36 sine squared theta is equal to 9x squared minus 12xy. This square bracketed term was cosine theta. I just showed that here. Plus 4y squared, which is exactly what we had to show here. Hence proved. So now I'm going to do question 3 part B. So the question you could do instead of that proof. So it goes like this. You have cosine of 2 times cosine inverse of x plus sine inverse of x. Given this, you have to evaluate the expression at x equals 1 over 5. So instead of just plugging in 1 over 5, it will be really hard to do if we just plug in. I'll try to simplify this. So we have cosine of 2 times cosine inverse of x plus sine inverse of x. Now there's a nice identity. Cosine inverse of x is equal to pi over 2 minus sine inverse of x. Basically sine inverse and cosine inverse add up to pi over 2 because they are complementary angles. So we can do that over here. We have cosine of 2 times pi over 2 minus sine inverse of x plus sine inverse of x. So that becomes cosine of pi minus 2 sine inverse x plus sine inverse x, which becomes cosine of pi minus sine inverse x. Now cosine of pi minus some angle is negative cosine of that angle, which is sine inverse x. Now cosine of sine inverse is square root of 1 minus that angle squared. We still have the negative though. And now telling us to plug in x equals 1 over 5. So now plug in x equals 1 over 5. The expression now becomes negative square root of 1 minus 1 over 25, which is negative square root 24 over square root 25, which is 5, which you can still simplify to negative 2 over 5 times square root of 6. And that's the answer. Okay, so moving on to the next question, they're saying using properties of determinants, show that this determinant is equal to x minus p times x squared plus px minus 2q squared. So it's a proof, and let's start with the left hand side, which is this determinant x pq px q qqx. Noticing the x minus p factor over here, what I would like to do is I would like to do an operation, change row 1 to row 1 minus row 2. So when I do that, so it will be x minus p, p minus x, and a 0 here, and we have p x q q q x. Now we can plug out a x minus p term from the first row. So we get 1 pq negative 1 x q 0 qx. And after doing that, I would noticing the 1 and negative 1, we could, if we could add them, we could get a 0 over here. So change column 1 to column 1 plus column 2. So then we have x minus p as a factor. Now 1 minus negative 1 is 0, p plus x like that, q plus q 2q, negative 1x q 0 qx. And now since we have two zeros, it's a good time to expand by row 1, because we already have two zeros. We only need to worry about one other column. So when I do that, x minus p, negative negative becomes a positive, and we have x times p plus x minus 2q times q, which is 2q squared. So when I expand this, x minus p will become uh, x squared plus px minus 2q squared. Round this up if you want. That's exactly what our right hand side was equal to. Hence proved. Okay, so question number 5 is actually verifying Rolle's theorem for the function f of x is equal to cosine of x minus 1 on the interval 0 to 2 pi, both inclusive. So the first step for Rolle's theorem is to check for the conditions, whether the our given function and its derivative satisfy the conditions. So notice that f of x being equal to cosine of x minus 1 is continuous on the interval 0 to 2 pi, both inclusive. And it certainly is, because cosine of x is continuous wavy function, and minus x is just shifting it up by 1 unit, rather shifting it down by 1 unit. Okay, now let's take the derivative. F prime of x will become negative sine x exists on interval 0 to 2 pi, and don't include the end points, because you have a problem of left hand derivative and right hand derivative respectively on the end points. So always exclude them with these round brackets. So this means that f of x is differentiable at all x belonging to 0 to 2 pi exclusive, both exclusive. Fair enough. And we don't need to check for the third condition, which we usually do for uh, Lagrange's mean value theorem. But we need to check for one more condition, since this is Rolle's mean value theorem. So we need to check whether f of this one endpoint 0 is indeed equal to f of 2 pi, and it is some constant k. So if you plug that in, you have cosine of 0 minus 1, which actually turns out to be 0, and you have cosine of 2 pi minus 1, which also turns out to be 0, and that is 0 is a constant indeed. So since all conditions for Rolle's mean value theorem, Rolle's theorem actually, don't need the mean, are satisfied, therefore there exists some c on this interval 0 to 2 pi such that f prime of c, the derivative of f of x at c, is equal to 0. So we just plug in c in this f prime function. So negative sine of c is equal to 0, sine of c is equal to 0, and on the interval 0 to 2 pi, one nice place, exclusive, 0 and 2 pi are excluded. That's why the other place where c can be 0 is simply pi, and at that certainly belongs in 0 to 2 pi. So hence verified. RMVT or Rolle's theorem is verified. Oh, question number 6. But oh gosh golly, we have another proof. So we have to prove that y equals e to the m times sine inverse of x satisfies this differential equation. So anyways, what we're going to do is take this y is equal to e to the m times sine inverse of x. Take natural log on both sides. We have natural log of y is equal to m times sine inverse of x. Now differentiate both sides with respect to x. So we have 1 over y times dy over dx by implicit differentiation, and over here we have m divided by square root of 1 minus x squared. So dy over dx therefore is my divided by square root of 1 minus x squared. And it's actually worth remembering my is equal to square root of 1 minus x squared times dy over dx. So just remember this fact, it will be helpful later. Okay, we have this. Now what we are going to do is differentiate again with respect to x. That's because we had a second order derivative too. So we'll have d2y over dx squared is equal to m can be taken out. Now quotient rule, square root of 1 minus x squared times dy over dx minus minus we'll have just y over 2 times square root of 1 minus x squared and a negative 2x, negative negative positive 2x, like that. But all of that is still divided by the square of the denominator, which is 1 minus x squared, because we lose the radical. So the 2's will cancel out. We can take this on that side. We have 1 minus x squared times d2y over dx squared is equal to, we can take the LCM over here, square root of 1 minus x squared times square root of 1 minus x squared is 1 minus x squared times dy over dx plus xy all divided by square root of 1 minus x squared from this. Okay, now let's split this up over subtraction. We have m times square root of 1 minus x squared times dy over dx plus my times x over square root of 1 minus x squared. And now this is the point where we actually remember this important fact that we had. My is equal to this expression, so we can substitute that. So the square root of 1 minus x squared times dy over dx is my, that's here, so this is my. 1 minus x squared times d2y over dx squared is equal to m times my, which is m squared y, and then my is square root of 1 minus x squared times dy over dx with this x over square root of 1 minus x squared, like that. Best part, these cancel out, so we have 1 minus x squared times d2y over dx squared, take that on that side, is negative x times dy over dx is nothing but m squared y, hence proved. Okay, so for question number 7, you could again select between A and B. Could choose. So let's do both. First, let's do A. So it's saying the equation of tangent at 2, 3 on the curve y squared is equal to px cube plus q is y is equal to 4x minus 7. Find the values of p and y, p and q. So we know the equation of tangent at 2 comma 3 is going to be y is equal to 4x minus 7. And the tangent on this curve, the tangent part is tangent to a point on this curve y squared is equal to px cubed plus q. So to find the tangent line, or the slope of the tangent line to be precise, let's differentiate with respect to x. So we have 2y times dy over dx is equal to 3px squared. So now let's plug in 2 comma 3. So for x plug in 2, for y plug in 3. So 2 times 3 6 dy over dx is 3 times 2 squared is 12p. So this implies that dy over dx is equal to 2p, and this means the slope of tangent line at this point that we plugged in 2 comma 3 is 2p. But they say that they've given us an equation of the tangent at 2 comma 3, so both of their derivatives should match. So take out the dy over dx of this, you just get 4. It's a linear equation. So since both dy over dx at 2 comma 3 tell us the slope of tangent line at 2 comma 3, 2p must equal 4, right? Because both of them are representing the same thing. So this means that p is equal to 2, which is indeed the case. Okay, so we know something is 2. Plug it into this equation number 1. So we have y squared is equal to 2x cubed plus q. Now plug in 2 comma 3 because we need to again solve for q. So we have 9 is equal to 2 cubed is 8 times 2 16 plus q. So q is nothing but 9 minus 16, which turns out to be negative 7. So we know that p equals 2 and q equals negative 7. Okay, so the other option you had instead of A was B for question number 7, which said using L'Hopital's rule, evaluate limit as x tends to 0 of x times e to the x minus natural log of 1 plus x over x squared. So if you plug stuff in, x times e to the 0 times e to the 0 will be 0 minus natural log of 1 plus 0, natural log of 1 is 0. So 0 minus 0 over 0. So this is an indeterminate form of 0 over 0. So which means we can apply L'Hopital's rule. So let's do it anyways. So apply L'Hopital's rule. Our limit now becomes limit as x goes to 0. Differentiate this, you get x times e to the x plus e to the x minus 1 over 1 plus x over 2x. And again, if you plug stuff in, you'll have 0 over 0 indeterminate form again. So apply L'Hopital's rule again. You have limit as x goes to 0 of x times e to the x plus e to the x plus e to the x plus 1 over 1 plus x, the whole thing squared, divided by 2. Now when you plug in x equals 0, this term goes to 0. You have 2 times e to the 0, which is 2, plus 1 over 1 plus 0, which is 1, all divided by 2. And that you can easily simplify to be 3 by 2 or 1.5. So I guess that's it for this video, guys. We did till question number 7, which is basically exactly half of section A. We'll do the other remaining 7 questions in a part 2 video. So stay tuned for that. In the meantime, stay home, stay safe, keep doing math. Peace out. Oh yeah, and don't forget to like, share, and subscribe to my channel and follow me on Instagram. That's really important. I'm putting in a lot of work for these videos.